Did you know that you can light your soil on fire to find out what's in it? Okay, it's not that simple, and you should really be careful with fire. But chemists use a process called combustion analysis to help them understand what compounds are found in a variety of mediums, including soil. Our soil is affected by so many of our activities. One such practice that impacts the soil is fracking. Fracking is the process of extracting oil and natural gas from underground rocks. Fracking is controversial mainly because crude oil and natural gas deposits contain harmful chemicals such as benzene, toluene, ethylbenzene, and xylene. These are called the BTEX compounds. During fracking, these compounds can be released into the soil and groundwater supply. BTEX compounds in the groundwater can be a problem because these compounds can harm humans. For example, benzene can cause cancer. Here's where combustion analysis can help us. Combustion analysis involves burning a sample with added oxygen and analyzing the resulting gases. Carbon and hydrogen atoms are neither created nor destroyed during the reaction with oxygen atoms, so the same quantity should be present in the products. If we were to combust benzene, C6H6, in a soil sample, it would react with oxygen and form carbon dioxide, CO2, and water, H2O, as products. To determine the quantities of carbon dioxide and water produced, we need to think at the atomic level. Since benzene has 6 carbon atoms and 6 hydrogen atoms, when fully combusted, it will produce 6 CO2 molecules, each containing 1 carbon atom, and 3 H2O molecules, each containing 2 hydrogen atoms. Oftentimes, we don't actually know which compounds are present in a soil sample. If we didn't know there was benzene in the soil, how could we determine what is present? Here, we must use experimental observation to guide us. Combustion of an unknown sample typically leads to some amount of CO2 and some amount of H2O. Let's take a look at an example in which we don't know what's in the soil. Suppose we obtain 6 CO2 molecules and 6 H2O molecules after combusting our sample. We can then conclude that we started with 6 carbon atoms and 12 hydrogen atoms by counting the molecules and their respective atoms. In this case, we know that benzene is not present in our sample because benzene left us with 6 CO2 molecules and 3 H2O molecules after combustion, whereas this sample produced 6 molecules of both CO2 and H2O. In both the benzene and mystery samples, we have carbon and hydrogen. It's not the absolute amounts of carbon and hydrogen that is important in combustion analysis, but their ratio. 6 CO2 molecules with 6 carbon atoms and 6 H2O molecules with 12 hydrogen atoms is a ratio of 6 carbons to 12 hydrogens, which can be simplified as a ratio of 1 to 2. Suppose I took a sample from the same source as the mystery sample that was twice as large as my initial sample. Everything would be doubled. The combustion analysis would contain twice as much CO2 and twice as much H2O, which would lead me to conclude that I had twice as much carbon and hydrogen. If I took a sample half the size, I would have half the amount of carbon and hydrogen. In either case, the ratio of carbon to hydrogen would remain the same. It's 1 to 2. However, simply having this ratio does not allow us to specifically identify the molecule. Why is that? If I did a combustion analysis of cyclohexane, which is C6H12, I would obtain a ratio of 1 to 2 for carbon to hydrogen. But if I did a combustion analysis of cyclopropane, which is C3H6, I would also obtain a ratio of 1 to 2 for carbon to hydrogen. So, based on combustion analysis alone, We cannot differentiate between C6H12 cyclohexane and C3H6 cyclopropane because they both produce the same ratio, but it does slightly narrow down our options. In chemistry, these ratios are given through the empirical formula. When we utilize combustion analysis on C6H12 and C3H6, both result in a 1:2 carbon to hydrogen ratio. Thus, they have the same empirical formula, CH2. Since more than one compound can have the same carbon to hydrogen ratio, the empirical formula alone does not provide enough information to distinguish between different compounds. In order for us to determine whether or not our sample truly contains cyclopropane or cyclohexane, we'd need a bit more information. Thankfully, we chemists have multiple instruments in our scientific tool belt. This is especially important when our mystery compound could be a potentially harmful substance in our soil. The ability to form a more complete picture of the compounds in our investigations aids us in making our environment safer.